Good morning, ladies and gentlemen. The topic of my talk is the development of a Simusage model for the processing of lead and copper ores through the TSL process. My presentation will be divided into the following topics. At first, I will say something about the scope of the work. Then I will give an overview about the TSL process. Next, I'll explain something about the model structure. I go over to the model setup. At the end, I will show the results, and I will finish with the conclusions. The primary aim of this work is the development of a holistic thermochemistry-based model, process model for the TSL process. There are models for this process in the literature, but normally they are concerned only with parts of the reactor, not with the whole reactor. And the secondary aim is to use this model, this developed model, to optimize through simulation of product design and or process routes, at the end envisaging the recycling of strategic chemical elements. Why we are focusing the lead as a primary metal? The reason for this is that lead is one of the most recycled metals. The first reason. The second reason for this is because, according to the so-called metal wheel, many secondary metals can be recycled in association with the extractive metallurgy of lead. So all the elements in these green circles here can be recycled in the scope of the lead metallurgy when we consider lead as the primary commodity metal. The TSL process may be used to extract lead, zinc, and copper. The process is also known as Ausmelt TSL. It's a trade name by Autotech. The process is very versatile, so we can use we can feed into the process primary materials or secondary materials. And this process is also a compact and flexible one. So this is efficient relatively to the energy and to material resources. The process takes place in a vertical reactor. You can feed into the reactor a gaseous mixture through the lens. The composition of this gas may change during the process, but it can also change. It can also feed, basically. You can also feed solid material into the furnace. During the burning or during the reactions which will take place in the reactor, you can form different products which you can take out of the furnace through holes on the sides. On our case, we are focusing on the lead metallurgy. And in this process, you have basically three stages: the smelting stage, the slag reduction stage, and slag fuming stage. Each step of this process occurs under different conditions. We are focusing on the smelting stage. In this stage, we are basically converting the lead sulfide, which is contained in the lead concentrate, into slag, and into the bullion. The slag will be, after this step, the slag will be converted into the bullion in this stage, in the slag reduction stage, but it's not the focus of our work now. Our focus now is only to study, to investigate, and to model this smelting stage. So the process occurs like following. The concentrate plus fluxes are fed into the smelter. And then by blowing the oxidizing agent, which is really enriched air, air enriched with oxygen, just below the surface of the charge, you form the following products or zones in the furnace. The first one is the bullion zone, where the metallic lead will accumulate. The second one is the so-called slag matte bullion interface zone, where the matte phase may form. The third zone is a slag zone, which, so to say, when you consider the whole bath, the slag zone normally is the most part of the bath. In the region where the gaseous mixtures impinges on the surface of the slag, you form a bubble. There you have the bubble zone. The droplets of the slag will spill from the surface, forming a splash zone. And there is also a freeboard zone. Each one of these reactors, or each one of these zones, will be associated with a different reactor in our model for the process. The model is based on a flow sheeting approach. You have different kinds of elements in this flow sheet. There are the reactors, in this case, R1, which is the bullion reactor, R2, the bullion matte slag interface, the slag reactor R3, the bubble reactor R4, and R5, the splash reactor. I'm not showing here the whole flow sheet because it doesn't it isn't compatible with the space that I have available for the slide. So I'm showing only the main part of the flow sheet. During the calculation, in each time step or iteration, the whole flow sheet is calculated from the inputs to the outputs, and it runs more or less like following. The gas which comes through the lens can go to the bubble, R4, or can go to the slag, R3. So use for this is fraction splitter, which divides an input stream of gas into two input streams according to a certain fraction of mass. When the oxidizing gas coming from the lens arrives at R3, you form a series of products. These products are then separated according to the different phases. So for this, we use the so-called phase splitter. You have basically the metal phase, which goes back to R4, R2, the matte phase, which goes back to R2, the gas phase, which goes directly to R5. And everything else, like for instance, the slag and the solid oxides, they go on along this backbone, One part of the slag may go back to R2 through this fraction splitter, and that one, or may go back to R3. And 40% of the slag will go on and will react with the oxidizing agent at R4. We need, in this flow sheet, you need the iterators basically to describe the flowing of material from one reactor to another one, when material should flow from one reactor to another one over two different time steps. And the iterator is especially important in order to describe the settling down of condensed phases in the reactor. So the input materials that you have in the reactor are basically the concentrate, water, silica, and enriched air. The quantities are listed on the slide, and each iteration corresponds to 1.5 minutes. The reactor works at a temperature which is fixed during the whole process, but each reactor or each zone has a different temperature. Temperatures vary between 1000 degrees and 1150 degrees. And the main solid feed, which consists of the concentrate plus CaCO3 and indium oxide, which is an extra material which we add because you are interested in indium oxide. The main solid feed consists of this composition here. As I said, the total of solid feed which is entered into the reactor is 1,000 kilograms per iteration, but composition of the solid feed is given in the table. In order to have a stable process, you know from the practice that you should avoid the mat phase. You should have a oxygen partial pressure between 10 to minus 6.5 and 10 to minus 7.5, and the lead content in the slag should be between 35 and 50 weight%. When you calibrate the model by adjusting the split factors, basically for the fraction splitters, you get reasonable results. So you can see how the amount of the bullion phase grows with time. At the end, we achieve basically 600 tons and 800 tons for the 60 tons, 80 tons for the slag phase. The slag composition can be shown here on the right slide, so you can see how the slag composition varies with the time, and the amount of Pb in the slag is reasonable, and also the amount of zinc in the slag is also reasonable. It's interesting to notice what happens when we increase or decrease the amount of process gas for the original situation with the original concentrate. You can see that by decreasing a little bit the amount of process gas, it's possible to increase the amount of bullion, but one must take care because the mat phase is also increasing, which may lead to instabilities of the process. We should now substitute the original concentrate by concentrate which is purer in lead sulfide. It seems that the alba curves are being shifted to the right. And we would like to understand what is happening here in the situation. So to understand this, we take a look at the two situations. When you plot the log of the oxygen partial pressure at R4, that is to say the bubble, as a function of the variation of a process gas amount. You see that, quite interestingly, the quantity of bullion, or so to say, the point which corresponds to the maximum bullion amount, in the two situations corresponds to more or less the same oxygen partial pressure. But you also see, for instance, for a situation where you have 4% more process gas, in this situation, basically you have no mat phase, that there is a gap between the two curves. And the question is, why? I mean, why is the reason? What's the reason for this gap? To try to clarify this, you took a look at the phases. I mean, which phases do we have at the end of the process in each reactor, in each zone, for this situation? That is to say, for a situation you have 4% process gas, 4% more process gas than the original one, and for both scenarios, I mean, original concentrate and 5% pure concentrate. And you may see the amount of slag when you consider a concentrate which is poorer in lead sulfide, the amount of slag decreases a little bit. But most important is that the percentage of solids in the slag will increase a lot. So our hypothesis is that Once you have now much more solid phases, solid oxides in the slag than you have for the original concentrate, you are basically having you are fixing the oxygen much more effectively in the condensate phase, what leads to a decrease in the partial pressure of oxygen in the system. And of course, the whole reactor depends quite a lot on the oxygen partial pressure in the system. Conclusions: the model reproduces qualitatively and quantitatively the expected behavior of the phases and of the elements in the PB smelting. It can be used for the corresponding process optimization. Copper metallurgy could also be probably modeled. Simulations are an important step for the recycling optimization. And possible next step will be the considering of the influence of full addition. Thank you very much for your attention.